I want to look at one more example problem involving limits of compositions of functions, because this requires a little bit more than what we've seen in the theorem so far. So I think it's worth taking some time to look at. Let's try to evaluate the limit as x approaches 1 of arc sine or inverse sine of the quantity 1 minus root x over 1 minus x. Now, we had a theorem that said that when we have a composition of functions, if both of those functions were continuous for the relevant values, then the composition of functions was continuous. But the problem here is that the inner function is not continuous as x approaches 1. Because when we plug in 1 for x, we end up with a 0 in the denominator, and so the function is not defined at 1. So we cannot use the theorem that we had before that said that the composition was then continuous, because we can't just plug in 1 and evaluate what this is. But we do have another theorem that we can use when we're dealing with a composition of functions. Let's take a quick look at this. This theorem says if f is continuous at b, and the limit as x approaches a of g of x equals b, then the limit as x approaches a of f of g of x equals f of b. That is probably a lot to take in at once, but in other words, there's kind of a simplified version. The limit as x approaches a of f of g of x is equal to f evaluated at the limit as x approaches a of g of x. So basically, so long as the outer function is continuous at the relevant value, and the relevant value is the inner limit, but so long as that outer function is continuous when evaluated at that inner limit, it means that we can take the limit and pull it inside the composition of functions. So we can take the limit of the inner function and then evaluate the outer function at whatever that value is. So arc sine is continuous on its entire domain. So as long as we pull the limit inside and whatever we get is in the domain of arc sine, then we can evaluate this by pulling that limit inside. So I'm going to not go through the trouble of rewriting that. I'm just going to move down and say equals. By this theorem, this is equal to arc sine of the limit as x approaches 1 of that fractional function 1 minus root x over 1 minus x. So if we can evaluate this inner limit, then we can just evaluate arc sine at whatever that value is, so long as that value is in the domain of arc sine. So now we have to evaluate this inner limit, and we can't use direct substitution. We would have a 0 in the denominator. But there is a trick that we can use here. You can think of 1 minus x as a difference of squares. It is 1 minus root x times 1 plus root x, because 1 is 1 squared and x is root x squared. And so we can rewrite that denominator, and we end up getting 1 minus root x in the numerator, and then 1 minus root x times 1 plus root x in the denominator. And now we can cancel the 1 minus root x's in the denominator, which leaves us with 1 in the numerator, because 1 minus root x is the same as 1 times 1 minus root x. And then we can write out that simplified version. We've got the limit as x approaches 1 of 1 over 1 plus root x. And we know that root functions and constant functions are continuous on their whole domains. and that the sum of two continuous functions is continuous, and then the quotient of two continuous functions is continuous. And so because 1 is in the domain here, we can evaluate this limit by just plugging in 1 for x. So that's going to give us arc sine of 1 over 1 plus root 1, which is arc sine of 1/2. And so which angle gives us a sine of 1/2? That is pi over 6. So that is our limit. So in a situation where we have a composition of functions and we're trying to evaluate the limit, but that inner function is not continuous at that value of x, we can't use direct substitution, but we can, so long as the outer function is continuous, pull the limit inside, and then we can use some of the different tools for evaluating limits to evaluate that limit, and then we can evaluate the outer function at whatever that result was. So long as the outer function is continuous at that value, and arcsine is continuous at 1/2, so we're good to go.